In this video, we're going to talk about a couple of important vector operations. We're going to talk about the dot product and the cross product, and we're going to talk about the geometry of these things. So, let's start with a couple of vectors. Let's say I have a vector v, and it has three components. This is the x component, y component, and z component. And this is standard notation for looking at a generic vector. And I want to look at the dot product of the two. The definition of dot product, this is a little dot symbol, is going to be the first components multiplied together plus the second components multiplied together plus the third components multiplied together. One thing that I want to note here is that the output is a scalar, meaning that I start with two vectors. I'm inputting two vectors into this operation, and I don't get a vector out again. I just get out a real number. I get out a number that's some numbers multiplied plus some other numbers multiplied plus some other numbers multiplied. This is going to be a real number, and we'll call a real number a scalar. So, for example, what does this operation look like? This looks pretty complicated. It's much easier than that in practice. So I'm going to look at the first components. Here I have a 3 and here I have a 5. So I look at 3 times 5, and then I'm going to add to that negative 2 times a half. And then I'm going to add to that 0 times 4. So what do I get out? I get 3 times 5, which is 15, minus 1, plus 0, which in this case is 14. So that's the dot product of these two things. Why are dot products interesting, right? That seems pretty boring. It just gives us some number. Turns out the geometry of dot products is interesting. So by definition, and we can verify this doing a proof. I'm not going to do that right now in this video, but because it's important that we know how it functions. That v dotted with w is going to be equal to the magnitude or the length of v times the magnitude or the length of w times the cosine of the angle between them, where the angle, where theta is the angle between them. So let's think about this for a second. What does that mean in terms of values of the numbers that come out for a dot product? First of all, like here we're thinking in three-dimensional space. Let's sort of picture what it's like to have my vector v and my vector w somehow living in three-dimensional space. Here's my vector v, here's my vector w, and here's my angle theta between them. And if I could dynamically think, if v got longer and longer and longer, then the magnitude of v is increasing. That means that the dot product would increase. So as v and w both grow, the dot product grows. As v and w both shrink, the dot product shrinks. What happens with this angle between them? Recall that the cosine of 0 is equal to 1. Like on the unit circle, here's my unit circle. I always visualize this when I think about cosine. Cosine is the x value. So when I'm down here at 0, my cosine is 1. When I get up to an angle of pi over 2, the cosine of pi over 2 is 0, and if I continue around, the cosine of pi is equal to negative 1. So that means that for acute angles, for angles between 0 and pi over 2, my dot product is going to be positive. But for obtuse angles, my dot product is going to be negative. So I can think about maybe here also, let's say I have my angles or my vectors v and w, and they have a tiny little angle between them. Here's my theta 1, here's my theta 2. As this angle is small, my dot product is going to be positive. As the angle gets bigger and approaches 90 degrees, right at 90 degrees, the dot product is going to be 0. And then as the angle continues to open up, the dot product becomes negative. What are some implications of this? This means that, let's say I take a vector and dot it with itself. Well, what does that mean? That means that it's going to be v dotted with v. I get the magnitude of v times the magnitude of v times the cosine of the angle between v and itself. Well, that's just an angle of 0. And the cosine of 0 is 1, right? And so that means that v dotted with itself is just going to be the magnitude of v squared. Another property that's important to note is that if I dot two things with each other, that's going to be 0 if the magnitude of one of these vectors is 0, meaning it's not even a vector, it's just one that's all the way shrunk down. In order for a vector to have a magnitude of 0, it means that all of its components are 0. Or, more interestingly, it's going to be if the cosine of the angle between them is equal to 0. And that happens when the angle between them is pi over 2, or really negative 3 pi over 2, but that's weird to talk about in three-dimensional space. Usually we go with just the standard angle measures. So the implication is that the dot product of two vectors is equal to 0 if they are orthogonal for 0 vectors. So orthogonal just means perpendicular in three-dimensional space. The next thing that I want to talk about is the cross product. This is another operation on two vectors. So let's say again I have a vector v and a vector w. What is the cross product? Well, the cross product is defined to be the determinant of a 3x3 matrix. So we have to remember what determinants of matrices are really quickly. My notation, the cross product is just notated by this x, and it's the determinant of this matrix. The matrix where I, again recall, is the unit vector with one unit in the x component direction. J is one unit in the y component direction, and k is one unit vector in the z component direction. So let's talk about determinants really quick. Recall, you probably remember that to look at a determinant of a 2x2 matrix, that's just going to be the product of the main diagonal minus the product of the minor diagonal. When we expand to 3x3 matrices, we think of the first row and first column position as a coefficient that's multiplied by the determinant of this minor matrix. So in this case, the first part of my determinant is going to be I multiplied by the determinant of this little matrix, which is V2 times W3, minus the minor diagonal, which is V3 times W2. It's only the first piece. The next piece is going to be J times the determinant of the matrix that starts here and sort of wraps around the other side. Or, alternately, and this is the way that I like to think about it, it's minus the determinant of this matrix, the V1, W3, V3, W1. So that's going to be minus J times V1, W3 minus V3, W1. And then finally, plus K times the determinant of this matrix back here, which is going to be V1, W2 minus V2, W1. This is long and messy, and I don't want you to think of this as something that you memorize. I want you to think of it as the process of going through this. So let's go ahead and compute an example of this to see what this actually looks like and what the output ends up being. So let's look at V crossed with W. It's going to be the determinant of the matrix I, J, K, multiplied by, I'm going to write out my vector V next. Notice order does matter. We'll talk about that in a second. 3, negative 1, 2, and then my vector W, which is 1/3, 0, 1. So let's look at each component here. So the determinant of this is going to be I times the determinant of this matrix, which is negative 1 times 1, minus 2 times 0, which is 0, plus negative j. So maybe I could usually just write minus j, but I'll just write plus negative j, and that's the determinant of this matrix where I blot out the j column. It's going to be 3 times 1, which is 3, minus 2 times 1/3, which is 2/3. And then finally, I get k times the determinant of this matrix, which is 3 times 0, which is 0, minus negative 1 times 1/3, which is minus negative 1/3. And I can simplify this. I see that this becomes negative 1 times I, or negative I. This becomes 3 minus 2/3 is going to be 2 1/3, which is 7/3. So minus 7/3 j. The minus is coming from the minus j. And then k times minus a negative 1/3 becomes a positive 1/3. So that's plus 1/3 k. So this is a vector written in its standard basis form. And if I wanted to, I could rewrite this as the vector negative 1, negative 7/3, 1/3. So this is two different notations for the exact same vector. So this is our new vector, v crossed with w. Why is this interesting? Why is this helpful? Why do we make this new vector? Let's talk about some properties of our vector. The first property is that when you take a cross product, that new resulting vector is going to be orthogonal to both v and w, and it follows the right-hand rule. So, for example, let's say I have two vectors v and w, and in three-dimensional space, these vectors v and w are going to live on some plane, and I usually like to write planes like this. So picture this as like a flat sheet, and both these vectors are lying on this flat sheet. The new vector that results from this cross product is going to be something that it sticks outwards perpendicularly. And this is my new vector v crossed with w. So I'm thinking of this flat sheet, and this new vector is like popping up out of it. You can't really see 3 dimensions on this video, but we'll try. It's perpendicular to both the vector w and to the vector v. And what do I mean by following the right-hand rule? This is where the order of the cross product matters. That if I take my right hand and I put it in the direction of v, and then put it in the direction of w, and I curl my hand around, the new resulting vector is going to stick up out of the page the way that my thumb is pointing. So I'm going to try to draw that with this little cartoon hand. Right. So this is my cartoon hand, indicating that, so these are my fingers curling back around, that they start at v and they curl back around to w, and my new vector, the cross product vector, is going to point in the direction of the thumb. What happens if I cross them in the opposite order? That means that my thumb would be curling downwards. So that means that w crossed with v, I'm going to start with my hand pointing, let's see, this is harder for me to draw, but I'll try. My fingers are curling sort of in this direction, right? Because my fingers are going to curl in the direction that the vectors go in, and then my thumb is going to be pointing downwards. This is my right-hand rule for v crossed with w. Really, they're just negatives of one another. What's the other geometric implication? That the magnitude of the new resulting vector is equal to the magnitude of each of these things times the sine of the angle between them, which is exactly, well, similar to the opposite relationship that we saw before. That in this case, if v and w, so for example, if I look at the magnitude of v crossed with itself, that's going to be the magnitude of v squared times the sine of 0. But the sine of 0 is 0, which is 0. That means that if I dot a vector with itself, I don't get anything out. And as the angle grows between the two vectors that I have, the magnitude of the new vector gets bigger and bigger and bigger. So here I would have like a teeny tiny little normal vector. Oops, maybe you can see that. So this is my v, this is my w, and this is the cross product sticking out. And as this angle grows to become more perpendicular, the normal vector is going to get bigger.